Good afternoon, everybody. A warm welcome to all of you to the SAICE National Head Office webinar on the design and construction and maintenance of concrete permeable paving. My name is Madeleine Engelbrecht. I'm a transport engineer and I'm a member of the SAICE Transport Division. As I said, I'm a transport and traffic engineer, so my knowledge of interlocking concrete permeable pavements is probably less than dangerous. But rest assured, we have brought in the international expert on the topic, Mr. Dave Hine, and he's going to share some best practice for the design, construction, and the long-term maintenance of interlocking concrete permeable paving. It's no wonder we had over 1,000 attendees who registered. So this promises to be a really extremely informative webinar, and I'm sure you won't be disappointed. I just want to touch on a few house rules. Everybody's mics are going to be muted because of the high numbers and just the way this webinar is set up. But you're welcome to say hello. I've seen Peter Davies checking in already. You can check in on the chat with all your friends or just say who's who. If you're here, if you want to say hello, you're welcome to do that. If you do have a question that you want Dave to answer, please post that in the Q&A and we will see if we can get to all the questions. We're going to have a question and answer session towards the end of the session today. The event is recorded and you will receive a recording. You will also get a PDF file of the presentation. Dave's agreed to that. It's also CPD accredited. So everybody who is dialed in today only, not those who registered, but those who have actually stayed in today will receive a CPD certificate from SAICE. How the event's going to work is Dave's going to do a 90-minute presentation. We're going to try and break it up with a short interlude after 45 minutes just to make sure everybody's awake. We'll then have a 25 minutes of questions and answers. So that's all going to work. With that, I think I'm ready to introduce our speaker for today, Mr. Dave Hine from Canada. And we were just chatting as we got on now how amazing it is that we can have an international guest speaker at an event like today, and it's really free of charge. And we also have to thank Bosun for contributing to this today. So Mr. Dave Hine has been involved with structural and hydrological design of permeable pavings in North America for a long time. He's authored 18 papers and he's completed over 60 workshops and webinars on the topic. He is the chair of the American Society of Civil Engineers for Permeable Pavement Committee, and they have also published the standards on permeable pavements. He was a technical reviewer for an ebook on permeable pavements, and he's completed design, construction, and maintenance guidelines for many agencies in Canada and the USA. So I'm pretty sure this is going to be very, very interesting, absolutely fascinating. And without further ado, I'm going to hand over to Dave to take you through his presentation. He's also going to share a little bit more about his experience. And over to you, Dave, and welcome,
Great.
very welcome to South Africa on this beautiful day.
Oh, thank you so much, because it's so dreary and rainy here in Canada, but it's springtime here, so we're starting to see the grass and the flowers in front of my office here at home. And thank you very much, everyone, for joining us here today to spend a couple of hours talking about permeable pavements. As Mandy mentioned, I have about 35 years of experience in pavement engineering. I started out as a structural engineer, but ended up in pavements way back in the 1970s, and then had a very large interest in hydrology and water. Surprised I didn't get into that field, but ended up having the ability to combine both of them together. So that's been very good. I am a traveler. I like to travel a lot. My goal is to see every country in the world, and I think I've got to 90 or so far. I do a lot of work, volunteer work with a lot of organizations. We have the Transportation Association of Canada. It's our national transportation group, and I chaired the Pavements Committee there and a member of several committees, including education, workforce development, councils. I do a lot of work with the World Road Association, PIARC, out of Paris. I've been the Canadian representative on the Pavements Committee, chaired the Pavements Committee for 8 years, and then moved to the Asset Management Committee about 6 years ago. So I'm currently still members. I've retired from full-time work, or I call myself semi-retired, and my wife tells me that I shouldn't be using those two words in any context of my work because I am not semi-retired. President of the American Society of Civil Engineers back in 2018, got involved in the development of standards for ASCE. I'm a very, I like seeing things standardized so people are doing things the same way. We help prevent failures and things like that. So one of them was the ASCE 6818, which is a document basically that a technical engineering document that provides detailed information to help you design, construct, and maintain permeable pavements, permeable interlocking pavements in particular, and also was a reviewer of the ASCE book on permeable pavements. In fact, it looks like this. And we had a meeting last night because every 5 years we have to update these things. And so this is a really good piece of guidance on permeable pavements if you don't know a great deal about it. And then the ASCE standard is much more technical. So we're going to talk about this all today. We're going to go through a little bit of the background. I'm going to show you some examples, a lot of pictures. I'm going to show you different projects I've worked on around the world. And we'll talk about the design, the keys for doing proper design. Once we do have design, all pavements need maintenance. It doesn't matter if you're building asphalt or concrete or gravel or whatever, they all need some sort of maintenance. Permeable pavements are the same, they do need maintenance. One only thing different is that you have to also maintain the hydrologies. And then we'll talk about, have some questions at the end, and I'm sure we'll have some interesting ones. And if we can't get to them all, we can probably take care of them after the session. So with that, I'm just going to begin talking about the problem. And so permeable pavements are not something that the pavement engineers have driven. It's mostly stormwater people that have driven this. And so architects, landscape folks, stormwater engineers, we've always been wanting to help, we always had to control our water, particularly in urban areas, because we change what happens when we start to urbanize it and we make hard surfaces. And so this is a picture from the southern area of Toronto, the Don River going into Lake Ontario. One of the largest sources of fresh water in the world, and we can't have this kind of stuff, obviously. We have a thing here called the Flood Resilience Toronto project on the go right now, and literally hundreds of millions of dollars being spent to prevent that. This happened, I was in Boston, Massachusetts, when they got half of their annual rainfall within 12 hours. And so moving water will find a place to go. And in this case, you can see what happened to the road infrastructure when the underground pipes became overwhelmed and caused a damage in the road surface. Water quality is a problem. This is Lake Ontario. This is where I live in Toronto, Canada. And the water that you see coming out of there into the lake is coming from the Humber River. The city spent over $1 billion building underground tunnels along the riverfront, or the lakefront here rather, to be able to control this and then pump it back after the storm into the treatment plant, which is just to the left of that building you see there. And there are beaches here all along the front, and we have CSO, they're called combined sewer overflow sewers here. So you've combined sanitary and storm sewers, and because it's an old city. And so always we would get E. coli contamination and issues for folks afterwards. And so a lot of money was spent trying to control that. We do then have a lot of regulations of this. And in the last 10 or 15 years, the regulations that we have here have gone substantially different. We have to detain water on site. We have to treat water before it gets to the lake, like you see there. Requirements, this location here is actually from southern England, just south of London. I took pictures of there probably 15 years ago. And so all of this subdivision has all permeable pavements in all parking areas, all driveways. The roadways are actually asphalt. And there are no catch basins. There's no underground drainage. There's no underground piping anywhere here whatsoever. The UK has got some excellent guidelines on permeable pavements. They call them SUDs. And so you deal with the water where it lands, as opposed to what we used to do is put it into stormwater ponds and let it run into the lakes and things like that. So the goal here basically, well, first of all, permeable pavements, the oldest one I could find in Canada was in the early 1900s. So this is not something that is new. We built a lot of these things back in the 1970s. They were mostly looked like concrete blocks turned on their side. And the real push of these in North America has been, or worldwide actually, has been in the last 20 years. And so when we have soils that are sandy in nature, we're able to get our water back into the ground. Where I happen to live here, we get 90% of our drinking water from the ground. The subdivision that I'm in, my house does not have any runoff from my house. All the water that is in the gutters around the house end up in the ground underneath my house. I have stormwater fees that I have to pay to the local municipality here. My stormwater fees are higher than my water drinking fees. And so we need the water in the ground to be able to get it back afterwards to drink. And so you see a lot of these regulations happening all through North America here and Europe as well, in that stormwater fees are becoming the normal, not the abnormal. And so we're paying a lot of money to treat stormwater. So if we can get it back into the ground, this is a good thing. So we can turn what was part of the problem, which is a hard surface, into an open surface, and we can get it in and reduce peak flows. If we can deal with stormwater upstream and make less water go downstream, we can prevent huge flood events like you have in hurricanes, for example, in Texas and in Houston, Texas a few years ago. It was incredible. They had a meter of water in the streets. We can also reduce things like erosion, obviously, and typically if you slow water down, the pollutants in the water will fall out of suspension. So it's basically gravity works. So this is a good thing in all cases. The modern versions of permeable pavements, you'll see the words pervious, porous, and permeable, or PICP, permeable interlocking concrete pavements. They're all basically the same kind of idea, but each of the different trade industries calls their product something different. So the standard here is basically pervious concrete, porous asphalt, and permeable interlocking concrete pavements, or brick pavers and grid pavements as well. So different pictures there you see from different locations and places I've done work. Asphalt on the right, permeable pavers in the middle, concrete on the right, on the or left was the asphalt, and on the right is concrete paving. Components of permeable pavements, they all have typically the same kind of things under the surface. So we have, in this case, a PICP, permeable interlocking concrete pavement. And at the bottom, you'll see the soil subgrade, the natural ground that we build on. You may or may not have geotextiles in the permeable pavement system. I'll talk a little bit about those later. You may also have a drain in the system. In North America, we have lots of sandy soils at the coasts. We have lots of sands along rivers and streams. And where I live here, there's an old glacial lake that used to be bigger than Lake Ontario. So along that lakeshore, we've got wineries. We've got every winery's got permeable pavements in their facility because the water goes directly into the ground. There is no runoff. Most of North America are silty clays, things that have finer grained soils, which are less permeable. And so we want to control the water, and we don't want it to flood up over top of it. And so what we do is potentially put in some piping systems I'll talk about a bit later. The layer above that is the reservoir layer. This is the sub-base layer where we put most of our water. Think about things like railway ballast. That's kind of the size of materials. It's 50, 75 millimeter maximum size. And it has a high porosity. So we are able to store about a third of the depth of water in that layer, however thick we make it. We can't really build a pavement on that because it's very coarse. So then we put another layer on with smaller aggregate particles. We lock it into the surface, typically 10 centimeters in thickness. And then if you're building pervious concrete or porous asphalt, you place it directly on that layer. It's like a normal base for a normal pavement. If you're building pavers or bricks or grids, you typically have a bedding layer, a small layer, 5 centimeters in thickness, that you put the bricks or the grids on top of it, because that's a smooth surface, so you can build a smooth pavement structure. All the layers are permeable, not just the surface layer or any of the bedding layer, the base layer, and the sub-base layer are all permeable materials. We have three basic kinds of designs. One of them is full infiltration. This is where you have sandy soils or soils that can accommodate whatever rainfall you do get. And so this means the water goes into the pavement, it goes straight through it, and it goes into the ground below. It may build up in the pavement structure if you have very high storms, but eventually all of the water will drain into the ground, which is easy, very common use for permeable pavements. Where I live, probably 80% of North America is more of a partial infiltration type design. We build the pavement structures, we accommodate the traffic, we accommodate the inflow from hydraulic flow of water, and then we control it. And so we put pipe systems in the sub base or the subgrade usually, and we control the outflow either through a V-notch weir or through a bent up pipe, whatever, so we can control it. So at a very major storm event, we don't want the water filling up the pavement and going on top of it. Well, sometimes we actually design for that. So we control the outflow, and we may have outflow going from the pavement structure. So we call that partial infiltration. This is our most common type of pavement structure we build here. No infiltration designs also are very popular. No infiltration designs usually used for one of two reasons. In the UK, you see a lot of these because they have brownfield sites where they have perhaps an industrial area there that they've turned into a subdivision. And so they don't want water, this groundwater, or the grounds underneath may have some low-level contaminants in it. Excuse me. And you don't want water flowing through that and moving those contaminants. So they'll put a liner at the bottom. Liner is typically polyethylene. And you basically, all the water that goes in the pavement goes somewhere else because it can't get into the ground now. It's an impermeable liner. Also, this is very commonly used when you're trying to save the water and use it for something else. And I've done a number of these designs. In fact, the Olympic Village in Vancouver in 2010 incorporated capture, stormwater capture, put it in an underground cistern, use it to pipe water back out and feed the plants. And so it's a part of the whole system because they won't allow any water to leave their actual site, their actual construction site. And they also get leadership in energy, environmental design points and things like that for it. So they're permeable pavements are used all over the place. Most commonly in parking areas, alleyways, low volume roadways. So you see a couple of examples here. One of the early on things that I was always asking the botanists are, do trees and plants like permeable pavements or hate permeable pavements? And the answer was resoundingly, it's a good thing for the trees. We have less, roots have more places to go. They have more open spaces so they can grow well. They get a water source. And so typically the tree canopies turn better. We were trying to hope to kind of quantify that benefit at some point in time, but haven't quite got there yet. And so you take also areas where it's very difficult to put underground infrastructure, like the alleyway you see on the top, and where there's no catch basins, there's maybe some utilities below that, but they're relatively shallow, and turn them into a water conveyance. So we put water into it and we control where it goes. Sometimes in this case, it went out to the street and is going into the adjacent storm system on the main street. I'm working on a couple of projects right now in Texas that we're doing exactly this. And so it makes it look nicer. Obviously, it controls the water that's there. We don't have ponding water on the surface, and this is beneficial to everyone. Parking areas, this picture is from Colorado. This is for brewery. And for the life of me, I keep forgetting the name of the brewery, but they're very green sort of infrastructure folks. And so you have beer trucks with kegs and things driving across this pavement. Excellent location for these types of pavements is Colorado. This happens to be in the Denver area. And it helps to melt the snow faster that's there. Heat from the earth typically keeps the snow off the pavement surface. We have roadways. You see this, if you go anywhere you want to see in UK, Europe, New Zealand, you'll find a lot of roadways built with permeable pavements. They have no catch basins. They have no underground piping system. As a road engineer, this is really, really good. I like this because I don't have trenches that I don't get compacted properly, and I don't have settlements that occur and things like that. North America was very slow to adopt fully permeable roadway pavements. You see many more of these. You go down the Rhine River in Germany, and every single parking lot is going to be a permeable pavement because water gets right into the ground. A lot of places are like that. But we've been a little slower, but now we see a lot more low volume roadways, residential subdivisions, and smaller retail places using permeable pavement systems. This is a roadway in Alston Way, it's called. This is in California, Berkeley, California, a project I worked on about 10 years ago. We had an existing roadway that we ripped up and we installed a permeable pavement there. So we kept the existing curbs and sidewalks and basically retrofitted this. The soils, this is on the shores of the San Francisco Bay, which has huge requirements for outflow of water and what they can have. And so the city wanted to do this. And so we reconstructed this roadway, and I'll talk a little bit about it a little bit further on. Parking lots, some examples. Left-hand side there is one probably 500 meters from where I'm sitting. The one on the bottom left is from a car dealership about 10 kilometers from where I'm sitting. The one on the top right is a Holy Trinity Church in Oahu in Hawaii that I did about 7 or 8 years ago. And so this was a design build, a permeable pavement system. Lots of different locations here. You'll see I got some asphalt ones on the right, the bottom as well. A lot of paver systems, walkways. This is in the city of Toronto. It's actually a raised walkway, and it's got asphalt parking area, asphalt driving areas and permeable paver parking locations. More walkways, lots of different places. There's some concrete on the right from North Carolina and some other from Florida on the left. The opening slide was the one you saw on the right. That's from a alleyway in Longmont, Colorado. Again, probably about 10 years ago. So a variety of different kinds and styles and shapes and sizes and things like that. And they really help to upgrade the neighborhood when you do things like this. This was the long one on the right was on both sides of the downtown roadway where all the parking was behind the retail buildings. And so this cleaned up the area and made it wonderful for people to look at. Or in combination. So you've got regular pavers on the left on the walkway, and you've got permeable pavers between all of the tree pits, between all the tree locations. So lots of different places to use this. Again, more walkways here. Driveways, people's houses, we see a lot of these now because many of the municipalities like mine here is giving you stormwater credits back on your stormwater fees if you have permeable surfaces on your home. And so I said, mine, all of the water that lands on the roof of my house goes in an underground storage basin, basically under my house. We have rain barrels in my backyard. We've got permeable pavers in my driveway, and it cuts down almost 50% of my stormwater fee costs. So it's worth it to me. I makes my house look great. We use the water. I can't believe how expensive the water is here compared to where I lived in Toronto. The water prices I'm paying here are 5 times as much as the Toronto area because all of our water comes from the ground as opposed to Lake Ontario. Other ones, a few other kinds of permeable pavements. These are grass blocks on their side with grass in the surface. Not very permeable. Because you see green does not mean water goes in. If the grass is growing, it would be organic material underneath there. It would have some soil in there, and those reduce the permeability. So while these are popular old permeable pavements, you don't see very many places building these much anymore because they really they don't have a very high infiltration capacity. This is a house I rented on the beach in North Carolina. Sandy soils underneath, everything is permeable pavements. Where my wife takes the cat, the veterinary driveway, all of the water on their site leaves across this driveway and infiltrates before it gets into the drain system. So lots of different types of them. First important thing with permeable pavements is not every site is suitable for a permeable pavement. And everybody has to remember that. And so there are not that many people who do design work like I do in particular for this kind of thing. And so I always get people all excited about wanting to build a permeable pavement for a bus transit terminal in Dallas. And so not typically a good location for it. I'm not saying you cannot, but I'm just saying that, if you want to have success of keeping it as a decent pavement structure, you probably want to look at the site location. And so we always determine, whether or not a site is suitable for a particular area for a permeable pavement. So in this particular case, this is prone to flooding a lot. Maybe the permeable pavement can help the situation. And so we do like the adjacent shoulders of the roadway impermeable to take some of this water away. One of the first permeable pavements built in Calgary, Alberta. I was involved with the city of Calgary writing their guidelines, and I wouldn't let them build a permeable pavement here if I had a choice because of what they use in the winter to keep a grit on the surface because of their snowfalls that they have, and they don't remove snow; they wait for it to melt basically here. And so we changed the rules basically as to the site selection. Somebody found a location, thought it'd be good, and didn't really think about it very much. Other areas where you've got a lot of things like organic lease and stuff like that, they may tend to clog the joints between the pavers and can cause issues in the future. So there are many reasons why some sites are better than others. And so ultimately we come up with some guidelines. We want to make sure that it's going to work. This is a parking area at a college campus in Portland, Oregon. Wonderful site, combines both permeable and non-permeable surfaces. It's got supplementary drainage, so if there's too much water on the surface, it goes between the curbs, it gets into the underground drainage system afterwards and infiltrates into the ground. Ultimately, we want to make sure they're going to work. So one of the first things that we did with the ASCE guideline, as well as the ASCE book on permeable pavements, was identify things that are keys to a successful project. And so ultimately, we got to understand where water is going to go. Water will find a place to go. People will drive things wherever they want to drive things, big trucks and all kinds of different things. And so we need to understand those conditions as engineers to be able to design this so that it's going to work. In this particular photo, you're seeing a bunch of railroad rails that were put in as a cattle guard kind of a system to knock the dirt off of the winter sand off the vehicles' wheels as they drove into the parking lot, so we wouldn't contaminate the parking lot. Very simple feature. It alleviated the problem you saw on that roadway I showed you a few minutes ago. We have to be cognizant that it's a permeable pavement. The contractor has to understand what the guidelines are to prevent contaminants and things like that. So we need to have people that understand the construction to be able to build them properly. This doesn't matter what kind of permeable pavement is. They're all, need to understand. I need to understand how to do pervious or porous asphalt mix designs. I need to know how to do pervious concrete mix designs. I need to know how to install pavers properly, select the right kind of pavers with the right joints, and all of these things are very important. So we go through all of those details. On the left-hand side of the bottom, it's the craziest permeable pavement I designed, and it was for what's called the Battle Command Center in Colorado Springs, in Colorado, United States. And they wanted the Pentagon in the U.S. wants all of their facilities to be Leadership in Energy Environmental Design Silver certified, and all of them designed to the standard, and 25% of them actually certified. And so this was a large area where they actually put tents and things like that. And they asked me to be the designer, working under a geotechnical engineer locally. And their first idea was that we're going to have small military vehicles like a Humvee kind of thing. And I said, yep, no problem, we can design that. And then they became bigger vehicles, the Bradley vehicle, and they had big tires on it. Yep, I can design that. Then they came along and asked me if I could design a permeable pavement to handle an M1A1 Abrams main battle tank. And I thought, okay, but I'm not going to stamp this thing. I said, it's never been done. So they said, what do you want to do? I said, I build a test section. So we built a test section, and we drove a tank across it, and we spun it in circles. And if you Google YouTube for permeable pavement Abrams tank, you'll find a video of all of the engineers giggling watching this thing driving around on the pavement surface. So I'm a believer that anything can be done. I don't like people telling me I can't do something. And so in this particular case, we picked the appropriate paver, and the marks you see on the pavement are actually rubber from the treads of that vehicle being torn off by the paver. So it's not the pavers being damaged, it's actually the treads of the tank being damaged. Pavers are very, very solid, very high durability, high compressive strength materials. So it was actually causing issues with the tank. We needed to control water. This was from the largest pervious concrete pavement site in North America back about 10 years ago. And they took a parking lot and they turned it a stormwater pond, and turned it into a parking lot. There have hurricanes here in North Carolina. So when Hurricane Irene came along, the water underground started moving faster than it should have. That was not very well controlled, and it undermined the pavement. Literally, that catch basin you see there, the chamber is actually in the air above. I could crawl under there if I didn't want to get myself killed. And so we need to control the water. And so we do this through a number of different ways, and I'll touch on some of these things as we move along. We want to keep contaminants off the pavement surface. On the left side, you see the one from Calgary, and the right is another one from California. During construction, we don't want to clog our permeable pavement. This book here you see, Permeable Pavements, is written by the Environmental Water Resources Institute. I was a reviewer for this one. I'm on the current committee to update this. We had a meeting last night, literally, with 30 experts in North America, that we bring our knowledge together, and we talk about all kinds of permeable pavements. Excellent guide. It looks like this. I have it in front of me here. And we published this in 2015. 10,000 copies have been purchased through American Society of Civil Engineers. And it's a really good overview and a guideline for all types of permeable pavements. It has checklists in there that I'm referring to as I'm going through my presentation. Not the most technical in terms of design details, but it is a very good overview of that. And so here's where you're going to see some of these as I walk through them. These checklists are in those guides, and we have details about what we want to know. Where are we designing the permeable pavement? What kind of safety factors are we going to include in terms of performance, in terms of water infiltration capacity, in terms of structural capacity for the vehicles that we intend to have on top of our pavement? Where are we going to store the water? Where is it going to go? How do we discharge water? Is it going to go into the ground? Is it going to go into a pipe? Is it going to go into a stormwater pond? Is it going to go into a storm drain? Do we want to slow the water down to improve the quality of the water, to have fine particles basically end up at the bottom of the permeable pavement? Then what do I do about that if I'm trying to infiltrate water? So do I have a way to ensure that I maintain that infiltration capacity ultimately? And then what's the end use? So what kind of traffic am I going to have on it? Am I going to have people driving, dump trucks all over it with dirt and stuff on them? So all of these things are important during our design. Geometrically, I have never designed or seen the same permeable pavement twice. Usually they're built to the context of the site location. We may have geotextiles. You'll find as I go through the presentation, I'm not a big fan. I typically use them in areas where I really have to, but not just generally, because they can become a built-in failure layer for the pavement structure. Underdrain details, subsurface water flow, surface water flow. In my area where I live, we have frost in the ground, so we have issues of frost penetration potentially, maybe frost heaving. Not typically, because nothing in the permeable pavement is frost susceptible, but you may have to consider those things. What are the soils? If the soils are sandy, wonderful, great structural capacity, great infiltration capacity. What if they're clays? What if they're fat clays? We have very nasty fat clays in everywhere in the middle of North America, from Texas up to Saskatchewan and Canada. We still have permeable pavements there. I built a permeable pavement north of the Arctic Circle once. They wanted to be green. I asked them why, but I sure I can do that. I built a 6-meter diameter detention basin basically beside it to put the water in. And I said, it'll never fill up. I'll be dead before it fills up, because you don't get rain in the north. It's a northern desert of snow, so you don't really even get much snowfall, but they wanted to have a permeable pavement. Key decision factors, this is from the ASCE standard. We went through all of the questions that people ask and all of the things that may influence what you do during design, for example. So not getting into the details. If you have utilities under the ground, we have ways of dealing with those and protecting those. If we have slow moving vehicles, we have ways of designing and selecting the appropriate paver surface for the permeable pavement system. We have water volume elements here that you see, complex geometric conditions for the surface and what's underneath the permeable pavement system. Ultimately, all of these factors need to be considered, and there's a lot of them here. You'll get a copy of the PDF. You can read them in more detail, but I just wanted to point out that we have identified these things and made decisions based on each of these. About 10 years ago, I got really tired of people asking, is this a good idea for a permeable pavement? Or is this a good location? Is this a good location? And so I did a research project for the US federal government, Federal Highway Administration, which was on use of permeable pavements for highway shoulders. And we came up with a decision matrix. So this is an example of this decision matrix. It's got engineers like spreadsheets, sorry, but that's what we do. And so this is a spreadsheet basically that has considerations. We call them primary, secondary, and other considerations on the left-hand side. We have those questions I just showed you in the slides on the right-hand side, with A, B, and C being, a higher risk or a no risk, a middle risk, a high risk, for example. And all you do is you go through and you pick drop-down box, and you end up getting a color down the bottom right-hand corner that says, is it a good candidate for a permeable pavement? Could it be done? Or should this not be a candidate for a permeable pavement? And so this helps me to explain to people about why I think a site is a good candidate or a poor candidate. And this matrix, this one was done for the highway shoulders, but I do separate matrices like this for urban municipal roads or parking areas and things like that. So I call it a screening guideline, basically, to give you an idea if it works. And so we look at things. So this actually came from the project I did in Berkeley, California. Alston Way. The city gave me 8 locations where they wanted to build a permeable pavement, and they asked me to look at them and look at their suitability. So I drove around, made some notes with them all, came back to the city council, explained why none of them would be suitable. And they said, well, why? And I explained. Finally, I said, okay, tell you what, I'm going to document this and explain to you why it's not a great candidate. Ultimately, we went through this matrix, and here's the results. This is the actual results. And they had 8 original locations. You see that they've got points there, the totals ranging from 47.2 to 70 something, 73.2. And you only see one that has a yes beside it. And so that's basically our criteria. Was it was more than 75 points, it got to be a yes. And so then they have finally understood it all. So we use these things to determine whether or not it should work or not. I have 3 projects on the go right now in Ottawa, Ontario, close to where I live here. And they selected all 3. One was a park, one was a library, and one was a community center. And at the end, I rated the community center such that, it was not a very good candidate. And so they've used other LID type things to handle stormwater there, but the other 2 we designed as permeable paver surfaces. So they're going to be constructed this summer. And then I did another porous asphalt project in Quebec, which ended up selecting a library parking lot as well. So these are very useful tools to help you to understand whether or not you should or should not consider something for permeable pavement. And like I said earlier, though, I truly believe that just about anything can be designed. With enough time and money, whatever, you can pretty much accomplish anything. Permeable pavement design, we'll talk about this a little bit. I'm not going to go into great detail. I'm going to kind of hit the highlights here. So at least to give you an understanding that there are good design procedures out there for permeable pavements. There are guidelines that are developed by the different trade organizations, agencies like Interpave in the UK is the one on the left-hand side. The National Asphalt Paving Association from the US is in the middle. The permeable interlocking concrete pavement is in the bottom, you see there. You also see the ASCE standards. Many agencies have their own requirements for stormwater. It's just it's crazy in North America because every US state and every Canadian province does their own rules and regulations. And also in terms of things like drainage. It's while there are national standards, everybody has something on their own. So we typically have to accommodate different elements that are related to the structural design as well as the hydrologic design. The structural is pretty straightforward, and we've got good tools for that. The hydrologic is just frustrating sometimes because of the different things that people use, and they're using large tools and computer programs that are built for primarily for large sites like whole entire subdivisions, and they're adapting them for a small parking lot. And I have one of these that's just driving me nuts right now in Texas, in San Marcos, Texas, for the same reasons. So lots of good things. In the ASCE standard, we decided to demonstrate basically a design flow chart. So on the left-hand side, you have structural design, relatively simple. We use something different in North America than you typically see in other locations, but I'll touch on that later. Hydrologic on the right-hand side, there's always a design storm. There's always contributing water from the area around the permeable pavement. We always have to infiltrate it. So we have good tools for this as well, certainly. But ultimately, the goal here is to design a pavement that is just thick enough to handle the traffic and just thick enough to handle the water. And then we optimize that. And so when we optimize the pavement, it's going to be the least expensive of them. Excuse me. Simple structural design, I'll just touch on this. In North America, we use what's called the AASHTO design procedure for pavements. It's being modified for all different agencies that do this, and it's not hugely popular worldwide, but it's simple. It was based on what the Americans designed for the interstate highway system. So it was adopted here because people understood that design process, and so that's why we went with that originally. And this is more than 10 years ago now, probably closer to 15 years ago. We need traffic data. For any pavement designer, you need to have traffic data. And we don't care about the cars and the motorcycles and the mopeds and those kind of things. We care about the trucks and the buses. So the delivery vans, the larger transport trucks, the bus systems are the pavement killers of the urban environment. We need to know about those vehicles, how many they are, what their weight categories are, perhaps what their axle load spectra is, their what they call ESLs, equivalent single axle load count is for those vehicles. So we need to handle the traffic data. I mentioned we look only at buses and heavy vehicles, and in the AASHTO procedure, we do what's called an ESL. In the 1960s, late 50s, early 60s, when this was designed, they came up with this equivalent single axle load value, which was based on the legal axle load limit in the state of Illinois, where they built a test track back in the 1950s. And so they standardized it on an 80 kilonewton axle load. Our axle loads in Canada are higher than this, and certainly yours are, and certainly they are in Europe and other places as well. But that was the standard for them. And so what we would do, and we knew that it wasn't a linear relationship between load and damage, and so it was a exponent 4 type formula. So if you have overloads over the 80 kilonewtons, if it was 160 kilonewtons, it wouldn't be 2 ESLs, whereas 80 kilonewtons would be 1 ESL. It would be 50 ESLs. So it was again a polynomial type expression. And so if it was less than 80 kilonewtons, their standard, it would be much less. So we count these up basically on the vehicles. We look at classes of vehicles. We make estimates if we have to. We have actual traffic counts if we have them. We want to use these for our traffic input. Then we have resilient modulus. Pretty much every pavement design procedure on the planet uses a resilient modulus for the materials, but many use surrogates for the resilient modulus tests. So this happens to be a standard test in North America, AASHTO T307. You see a soil sample that is in a mold or in a contained mold there, and it's squeezed. When we squeeze down, if it squeezes out a lot, then it's got a low resilient modulus. If it doesn't squeeze very much, it's got a high resilient modulus. So that is the basic parameter for the structural design for the soils. You may see things like California bearing ratio, CBR. This was a poor man's resilient modulus test developed in California. The Army Corps of Engineers developed dynamic cone penetrometer, again, different tests. We now use a thing called a lightweight deflectometer as well. And so these tools help us to determine what the resilient modulus is. So that's our input value for the strength of the subgrade. No different than if we're doing a standard pavement design. But now we have to add subgrade infiltration design. So we have tests again where we go out and use double ring infiltrometers and other types of infiltration tests to determine how much water are we going to be able to get into the pavement structure. Well, in this case, it's a greenfield site, so it's very easy to get to the bottom elevation of the subgrade, and we can do the test directly on it. When I was doing the one in California, it was an existing roadway. So we literally dug test pits in the existing road, and we measured the permeability. We expected something less than what we got. We were actually quite pleased that we had roughly 15 millimeters an hour permeability of the soil. And so that's our input values. Then there are some safety factors in the AASHTO procedure, the credible reliability and serviceability. Won't go into the details of what they do, but basically they factor up the easels to more than you design it for to make the pavement thicker if you want to have higher reliability. So they're basically safety factors. We take all of these values, the easels for the traffic, we take the subgrade modulus, we take the safety factors basically, and we calculate what's called a structural number. Structural number in this case is a dimensionless thing, but we need to put units to it because we're going to look at thickness in a moment. So this, based on that amount of easels and that subgrade and those safety factors, I need 63 millimeters of structural number of strength. And how do we get that? We get that by multiplying the thickness of the layer times its strength factor, or basically it's a factor related to the resilient modulus. And so in this case, in order to get 63 millimeters, I have to take paving layer, which is typically 8 centimeter paver plus a up 2 centimeter bedding layer, 130 total, multiply it by its layer coefficient, it's called, its strength value, and we get 39 millimeters. That's not 63. I need 63. So how do I make that up? I put a base layer in, multiply it by its structural layer coefficient. I get 6 millimeters. Now I'm at 45. Still not enough. So then I take the remainder and I figure out how thick of a subbase do I need to accommodate the 63 millimeters. In this case, it happens to be 300 millimeters, 30 centimeters. So that's it. I'm done. Structural design complete. And this is exactly the same procedure that we would use in this design procedure to be able to design a regular pavement or a permeable pavement, either way. It's the same thing. So we thought this is kind of a little bit Mickey Mouse. And so North America is finally moving along to catch up with some of the other folks around the world, like South Africa and Australia and the UK, and going back to the roots of this whole thing, which is stresses and strains, and converting those stresses and strains to distress, to things that cause you to determine when the pavement reaches a layer, a status of failed. And so this is what we did with the ASCE standard. So we got together about 20 folks on the hydrology side, 20 folks on the pavement side. I chaired this committee for 5 years. I'm still the chair of the committee, but it took us 5 years to produce this standard. And in the middle of it, we decided, well, finally, North America is adopting stress and strain approach for pavement design. And so we said we should be doing this for permeable pavements, and we don't have this information. So we looked at things like accelerated loading and other ways of doing this, and the industry ponied up some money. And we were able to develop a structural design procedure based on strain for permeable interlocking concrete pavements directly, based on accelerated loading. And so this is the standard. It was published a few years ago, 3 years ago, I guess now. Every 5 years, we have to update this standard. So in 2 years from now, we have to go back and revisit it and update it with things that we know. Pavement engineers, hydrology engineers, both working together basically to come up with this particular standard. 80 pages. It is a technical standard. It is not this is what a permeable pavement looks like. This is more about how do I design it for strength and for hydrology. We went out to California. We hired the University of California, Davis, built test sections of different thicknesses of permeable pavements, used one of these accelerated load facilities, which by the way, was actually manufactured in South Africa and brought to North America. And we built different thicknesses of pavement layers. We did the best we could to design and construct this in a controlled fashion, installed strain gauges, installed stress plates, installed moisture gauges, and all of that kind of stuff. And then in the middle of a drought in California, we put millions of loads on top of this permeable pavement. Here's a quick example of what we found in terms of wet and dry testing. And we established a rutting criteria as failure of 25 millimeters, 2.5 centimeters from a straight edge placed across the pavement. And so we loaded it and loaded it and loaded it. And obviously the permeable pavement had different strength characteristics if the aggregate was dry or the aggregate and subgrade were wet. And so by using and doing both of these, we're able to combine the impact of loading. So a vehicle driving on a dry pavement is going to put different strain on it than a vehicle driving on a wet pavement. And so now we're accommodating the annual rainfall over an entire location. So the dry days and wet days, and combine them basically to come up with the criteria based on that 25 millimeter failure. So this is the results from a 650 millimeter base and sub base. We had 300, 650, and 850 or 900, I believe it was. We came up with design tables. We came up with an actual mechanistic approach using axial load spectra, and there's a tool that we developed basically to impose the rainfall on the pavement structure and accumulate for any failure mode from 20 millimeters, 25, 50, whatever you like, but standardized it in our standard. We don't like to have people using software because software can change things and whatnot. So this standard simplified it. It basically said, how many days a year is the pavement going to be wet? What is the strength of the subgrade in terms of resilient modulus? What is the traffic in terms of easels, in this case, on the left-hand side? And the table that you see in front of you basically are the thicknesses of the subbase. So this includes 8 centimeter paver, 5 centimeter bedding layer, 10 centimeter base layer, and then the remainder you see you select from this table. And so these are the tables that went into the actual standard. A design example, just to show you briefly how it kind of works, is that we look at the easels in this particular case, the traffic values, we look at the subgrade modulus, we calculate the number of days where there could be standing water on the top of the subgrade or in the pavement structure, basically. And then we apply our stress and strain factors to accumulate the amount of rutting that occurs. So again, not to go into great detail, you need to have some basic information about your storm data to figure out how many days your pavement is going to be wet. So these are things that come off the internet, for example, and we calculate this. We calculate the number of days there could be standing water on the subgrade surface. This is not just a function of the rain that lands on the pavement, it's a function of the subgrade and how fast water can be taken away from the pavement. And so we have to accommodate both of those two elements to come up with this ultimately 25 millimeter in terms of 25 millimeter rutting. So you look at the pavement structure, I'm designing for 200,000 easels. I'm designing for 10 to 29 days when the pavement could be wet, interior to the pavement structure, standing water. I look at the subgrade resilient modulus in this particular case in terms of its CBR and resilient modulus and MPa, megapascals, and it tells me I need 315 millimeters of subbase for this. And so that's my pavement design. So this is what the ASCE standard does. We then took a tool that was developed for the Interlocking Concrete Pavement Institute called Permeable Design Pro. And I was the author of this and the designer of this system for the ICPI folks. And this was a tool that was intended to take the standards, both the AASHTO standard and the ASCE standard, and to combine them together with hydrology so that anyone can do a permeable pavement design. So this thing has been in place now for 12 years. I think we've had this published. And we've included storm databases for Canada, the United States, and New Zealand. I've done one also for the Philippines. And ultimately, Bozen has talked to us about potentially updating this for storm systems or storm requirements in South Africa. And so we combine the two together with each other. It's a simple software program. It can be taught to anyone. I teach water resources folks, and I speak water resources, I speak architect nowadays and everything else, and so we can actually design the pavement structures. So This is basically looking at things like catchment areas. Where's the water coming from? In this case, I've got water flowing from the park onto the red part, which is the roadway. I've got water flowing from the sidewalk, which is the green portion at the bottom, onto the red, which is the permeable pavement on the roadway. And I've got water falling on the roadway itself. And so we combine all of those catchment areas and the water that falls on the pavement to be able to, that's our water inflow. So we need to know about that. And so this is a site drainage analysis that on the middle, it's telling you what's the rainfall. It's telling me my contributing area runoff. On the right-hand side, you get details of the depth of water in the pavement every 6 minutes or every less than a minute. You can choose whatever kind of time frame you want, and it'll track all of it. So we're doing water balance literally every less than a minute for the permeable pavement going out to 7 days long. So it's easy to be able to do this. And then we have criteria. We have a safety factor here. It says, don't let the pavement get more than 85% full. And so that's why you see that kind of magenta orangey area at the top. It says, don't let it go past that. I'm plotting in this situation, the 2, 5, 10, 25, 50, and 100-year design storms. And this one happens to say now, based on your design inputs and your factors, that this pavement will accommodate a 50-year storm period without overflowing the pavement or getting more than 85% full. Yet the pavement will handle a 100-year storm, but there will be water in the upper pavement layers, probably in the paver layer itself as well. Tons of details are coming out of this. Everything is documented. Everything is, all the equations are in here. All the grids that you have, all of the water balance, you copy, paste them into an Excel sheet, produces reports, produces details on the permeable pavement system. And so it's been very successful. And again, more than 10,000 copies of this has been used out there, and it's not very expensive. But it has to be adapted sometimes to the local folks and what they do in terms of their rainwater systems and values and things like that. The New Zealand folks, I did workshops for them years ago and in different cities throughout New Zealand, and I adapted it before I went there to use their new rainfall data that has safety factors in it based on climate change that's coming up. And so they were impressed. I was able to do that. So it's not that difficult to make some of that happen. This is a link to the software. If you just type Permeable Design Pro in Google, you'll find the thing anyway. All right, so that's enough about design. Design is a little more detailed than that, and I do longer sessions certainly just focus on design and case studies and things like that. But to give you at least a taste of this, I'm going to get a little bit into construction now. So this is obviously extremely important. I am a geotechnical materials engineer that used to own one of the best materials testing laboratories in Canada. I am a construction guy. I'm on a one-man retired show now to try and teach people how to inspect construction, because mostly people are stupid, quite frankly. And we have gone so far backwards in our quality of our construction work in North America, at least, that we don't even have people that understand how a paver works, or how you make an asphalt mix design, or how you ensure that you're going to get a decent permeable pavement. And so training is always important. And a lot of the work that I do now is actually become the inspector or the trainer of inspectors and do training courses for people for all of the things you need to look for. And it's mostly conventional pavement stuff with a few twists based on the permeable pavement. So key things for construction is that one thing is we need to keep the site clean. What you see on the left was from a brand new parking lot in a college campus, where you couldn't even get into the parking lot, and the people that were doing the landscaping were dumping soil on the permeable pavement. No one told them that this was what it was, until finally one of their foremen came over and asked me. The one on the right is from the Russian River Valley in California. I drove by that, and I stopped the car, drove back. The wife says, what did you find? Another permeable pavement? Yes, I did. And I said, this one's good. Somebody was doing maintenance, and they actually put soil and stuff down on tarps on top of the permeable pavement. So it's not difficult. It's very simple. It's just people need to understand that it's a little bit different than a conventional permeable pavement. Checklist, this came from the ASAE standard as well. Again, things to do, looking at an erosion and sediment control plan, building a mock-up. Finished a Quebec permeable porous asphalt pavement in October of last year. And I made them pave a section, to show the contractor that this was different than their normal paving operation, and paid off in spades. We needed to make sure that they understood how to do this. Methods, what is the contractor doing? where are they getting materials from? How are they bringing materials in? Again, not different than a conventional pavement, but it needs to be all the details. It's always the details that cause potential problems in the future. It's not the basic stuff. It's the little things that always cause issues to occur. And then people say, "Oh, permeable pavement doesn't work," and that's just not the truth. Um, Contractor certifications. We have certification programs here for people laying permeable interlocking concrete pavement. The ICPI folks have a certification process that's specialized for PICP. The National Asphalt Paving Association has one for asphalt inspectors as well, and people that actually build permeable pavements, and they give you certificates and things like that. And you ask for these to make sure that the person that's on the site is actually one of the ones that was on that certificate and learned how to do this stuff properly. We need to prepare the site. We need to make sure that people understand, the layers that go in, how we put them together. You can't do little bits and pieces of this and that. When you do the surface, you do all of the surface, not just a little small piece and then add another piece and another piece. And this was one of the problems I had with the Olympic Village site, because everything was piecemeal. And it's very difficult, even on a regular pavement, to build a pavement that's not using uniform techniques and materials and things like that. Sediment management in the bottom right-hand corner there, we actually had a wash station built before they would allow them to get to this site. And it was a big Toyota plant facility, big, huge parking lot area. So it certainly warranted something like this. How do we deal with sediment that may wash onto our permeable pavement? We put up barriers to this. We have to do this anyway because of our environmental requirements here now. We put these sausages that have straw in them and stuff like that everywhere. We make sure that the water will flow away from the permeable pavement and not to it. And that can be also a design factor on the pavement section. So it's all about just thinking about the surrounding area. I remember one in Atlanta, Georgia. They built 10 kilometers of subdivision roadways out of permeable pavements to alleviate a low-lying area flood problem. And the permeable pavements were the choice because it was less expensive than finding and digging an underground tank to store water as well. And we built this, and then someone was putting up an apartment building and they were washing their concrete truck out, and the wash water was going around the corner and across the permeable pavers. That's unacceptable. We made the contractor for that job dig up the permeable pavement and replace it. They paid for it. And so, we have to follow the rules basically to ensure that we have the best chances of success. Permeable pavement against buildings. So these are some of the details that we have in our ASCE standard. Can people say you can't build a permeable pavement within 3 meters of the foundation wall? Well, I say crap to that. How can I build a alleyway on a behind houses and things like that when it's right up against the foundation? So we have details in the ASCE standard that we got from people who have been doing this for many years, and we then codified them into this ASCE standard. And so this is how we protect the walls if we need to. We look at things like downspouts and drainage things coming off of roofs of buildings. And typically we do not want water to flow directly onto our permeable pavement. It may wash away the joint material that's in it. It may cause undermining of it. So we have underground systems basically that takes the water from the top of the building and then distributes it in a diffused fashion underneath the pavement, inside the pavement itself. So lots of good details there. Subgrade preparation. This is one that's kind of a little bit controversial in terms of the fact that in the early days, at least, I would see specifications that said, when you build the permeable pavement in the subgrade, don't compact the subgrade, take the fingers from a excavator bucket and loosen up the surface. And the reason for that was to promote water infiltration. I'm a pavement guy. If you're going to not compact your subgrade, my pavement surface is going to start sinking. It's going to, you're going to get consolidation happening and stuff like that. And so I do not like this at all. I will always compact my subgrade properly like a normal pavement structure would be. If my subgrade is not very prone or open to infiltration, then I'm going to move the water someplace where it is more prone to infiltration, in an infiltration trench or other things, or a larger area. I may increase the area of the permeable pavement, and we built a golf course beside it. And underneath that golf course is an infiltration basin made of open graded aggregates that was an extension of the permeable pavement that allowed more water to infiltrate over a larger area. And even though the infiltration rate was low, we were able to get it in through the pavement structure. So lots of things like that can be done. So it's better than not compacting your subgrade. So I don't like that at all. We have things like check dams for slope subgrades. So in this particular case, we've got a situation where we've got on the left-hand side an alleyway again, and this was built in Richmond, Virginia, following UK specifications that used to use concrete baffles, basically. And I don't like these because they tend to reflect to the pavement structure afterwards, and they're expensive and things like that. So we learned how to make baffles out of an impermeable liner, basically, using the same aggregates we would use in the pavement structure. And so you see this case, you've got an aggregate. We put the baffle over top of it with the liner. We put some holes in the liner in some places to control a little bit of water to make sure it always goes away, but the water has to go downhill and then up and over and up and over the baffles that are under there. And they work extremely well and are very inexpensive to construct. This is the liner for the Olympic Village parking lots. And so in each of the parking areas, they put in an impermeable liner under the pavement structure to allow water to be captured. And those green pipes you see on the right were then taken to a cistern underground that was used to pump back and fill in the, basically feed the plants and stuff around the buildings. The only problem with this is I took that picture and I was watching this guy put the liner down, and the concrete curbs had some rough edges on the bottom, and he was puncturing the liner as he was putting it in. And I asked this guy, what's he doing? He goes, I'm putting a liner in. I said, well, what's the liner for? And he says, I'm not sure. I said, it's to capture water. And then he looks at the holes in the liner and said, that can't be good, right? That's right. That's not a good thing. They didn't connect the pipes to the liner very well as well. So it's important to have these details and not to destroy them during construction, for example. Geomembranes, use of geotextiles, I mentioned, I'm not a fan. They are very difficult to use during construction. I don't like them within the pavement layer itself. I will put it at the bottom to separate the larger stone from, say, wet, clay subgrades, because I don't want them to mix with each other. It reduces my structural capacity. Picking the right one, they need to be protected, the liners during construction. So sometimes we actually put the liner down and then put another geotextile on top of it to protect it when the aggregates are being placed on top of it. We may wrap utility lines and things like that as well. So lots of different ways that we can make this work. Under drains, you saw in the early graphic I showed you, there was actually a drain in the pavement layer itself, and I don't do that anymore at all. We put the drains in the pavement structure in the subgrade, in the top of the subgrade usually, the low point where water is going to go to, and then cover it with an open graded aggregate. And it's narrow enough so that you can actually drive a construction vehicle across it without damaging it. That way we know they're not going to be damaged during the compaction process of the sub base and the base layers. And so you see the guy there on the right hand side socketing it basically into the ground. So that typically will work a bit better. Key construction features, again, these under drains, they need to have an outlet. They need to have a slope to them to make sure that they're moving someplace. You need to make sure the pipe spacing is sufficient to allow, we design the number and sizes of the pipes to handle the water that's in the pavement structure specifically. So that permeable design program will allow you to determine whether you're using a corrugated pipe, a smooth pipe, a 100 millimeter diameter, 150 millimeter diameter, what the slope is going to be, how far the water is coming to the pipe system, how many pipes I have in there to take the water away, and all that kind of stuff. So that's the underlying portion of that. We also like to do this. We put some observation wells in the pavement structure. And so this is basically to determine what the depth of water is in the pavement, which is easy, and to take samples for environmental testing of the water quality, for example. The one you see in the picture in the photograph in the top is actually in pavement one. I don't like those because they interrupt the pavement surface and you put little pieces of paver around them. The one in the middle where it says outside the pavement is my preference, and we have both of these in the ASCE guide. But I prefer that one because it is exactly the same thing. It just offsets the location of the access point. And so it's not going to disturb my pavement. It's going to be in the grass beside it or something like that. It is top of the hour right now, so this is going to be a forced 2-minute sit up, stand up, get things shaken in your legs or whatever you need to do to at least take a short break so I can not sit all the time today. Hey, there we go. Awesome. Yeah, a little bit of stretching. I need to do that too. I do a lot of training stuff and end up sitting here and then I can't stand up after that. It's really kind of difficult to make that happen. So, all right, so we'll continue moving on here. So observation wells, great little simple thing. I have seen brand new pavements that are poorly designed and they're full, and I lift the lid on it and I can see the water coming out of the drain pipe there, the observation well, which is obviously not a good thing either. The materials that we use. The next two photographs were sent to me by a colleague in California, in North Carolina, and the aggregates that we use. We want decent quality aggregates. We want them typically to be angular. We don't want them to be rounded. We want them to be relatively clean, low fines content. I'm moving water through the pavement structure, and so I usually calculate, based on the fines content, how much material is going to end up moving through the pavement and explain it to people. It is literally, hundreds or thousands of kilograms of material, and I'm saying that's probably not a good thing to put in a permeable pavement. This colleague asked this guy if the aggregate were washed at the quarry. Yeah, yep. The driver says, yep, they washed the aggregate. So he says, let me see. Raise your bin in the back up a little bit. I'm going to get some water and I'm going to spray it over your aggregate, and I'm going to look at what comes out the back of your tailgate. And this is basically colored, pale colored material, which obviously has lots of fines contents in it. So he takes this and tells the guy to go back to the quarry and get me some stuff that was actually washed. So ultimately, the aggregates that we use, we want to use locally available materials always. We don't want people to construct something using an aggregate that is, from the ASE. ASE standard has what we call is a US and a Canadian standard for aggregate sizes. And so in the US, you call it ASTM number 8, number 9, number 89. Each of those has a different gradation. In the ASE standard, we talk about the physical material properties and all of those things that we want to have. But if I ask somebody in Canada for an ASCE or an ASTM number 57 stone, which is a kind of a 25, 30 millimeter aggregate size, they won't have no clue what I'm talking about. And so, some people have got them to make something like that. So they would specially crush it. And you don't want to do any of that. You want to use local aggregates, local specifications. You want to select materials that are going to meet the requirements of the permeable pavement. And I change my aggregates all the time. I always want to see what do you have for rail ballast. People are building railways, they have rail ballast. I use that a lot for my sub-base layer. My layer below is usually an open graded, similar size aggregate with maybe a little bit of grading to it. I've looked at some of your specifications and see some materials there with concrete materials from a concrete plant are very good in the smaller aggregate sizes, particularly for the jointing materials or the bedding materials. I've looked at your asphalt specifications and the lower, not the surface layer, but the lower layer below, the coarse portion of that, so the kind of 4 or 5 millimeter and higher aggregate gradation is perfect for the base layer. And so I always want to have something that's local because it obviously is going to have the least cost associated with it. When we compact it, everybody uses, or most people use, a standard Proctor maximum dry density developed by Proctor out in California back in the 30s or whatever it was. And ultimately, you cannot use a nuclear density machine that you poke the rod into the ground because of the open graded nature of it, you're going to get all kinds of variable results. And so we started by establishing target densities, and we would use a nuclear density gauge in its backscatter mode. And so we'd do a couple of passes, we do a test. We do a couple more passes, we do a test. We specify the rollers or the plate compactors and the force that they apply to the aggregate materials. And so we would go again, do a few back and forth, back and forth, back and forth, and we'd check to see, is the density changing more than 20 kilograms per cubic meter? If it is more than that, then we're going to go and do a couple more passes, and we establish how many passes you have to make. We don't want to overcompact it. We don't want to put too much vibratory compaction in it. I like to vibrate the first pass or two, and then after that, no more vibration. The aggregates are not like normal aggregates because they're open graded, and so the rocks each touch each other. And if you really pack them down, they're going to pass by each other and they're going to grind each other up basically and generate fines. So we don't want to do that. That's not good. When we were doing the test section in California, we started using a lightweight deflectometer, an LWD. And so we added this to the specifications. In the ASCE standard, we have guide specifications as well. And we talk about the Proctor method kind of thing with the test strips. And then we also talk about the alternative compaction testing using one of these guys. And there's been a lot of research on this here. And actually, I would specify this all the time pretty much. It's much faster, easier, can do more tests. And It's much more uniform, and uniformity is what we want. We really want uniformity of the compaction material. If we don't have uniformity, we get things like this. This is a settlement near a pharmacy in the US, where the concrete area was a pad for handicapped folks, and then the rest of the parking stalls were permeable pavers. And you can see the settlement in the corner because obviously they didn't compact very well. We want to deal with transition points. We don't want the transitions to be at low areas, because low areas are where the water is going to go. And if you can't get the water into the ground, it may pond on your pavement surface, obviously. We want to make sure that we are screeding the surface layer, the bedding layer properly, to ensure that we're only putting down 40 to 50 millimeters, not 60, not 80, not 5, but 40 to 50. When we compact it afterwards, we want to make sure that the pavers all sit nice and tight down into the surface and not going to cause issues further down the road. Different ways of doing screeding. Larger areas you do like this. You may have a little bobcat here pulling a more mechanized screed. I've seen screeding of bedding layers done through a paver, a spreader, an asphalt spreader, for example. And so again, all of these details are things that we already know, and we just need to make sure people understand how these things work. Edge restraints. All segmental paving systems need an edge restraint. If it is a transition between something like asphalt and pavers, as you see on the top right, I like a curb, concrete curb. If it is a driveway, sometimes we use those plastic or aluminum edge channels you see on the left-hand side there, and he's basically screwing them into the ground below. We need to have those edge restraints certainly to ensure that we're not having movement. It's called a segmental paving system because all of it needs to work together. We need to have the proper pavers. We need to have the proper space in the joints. We need to have the proper jointing material. This is not like conventional pavers. We don't use sand in the joints. We want water to infiltrate through them. A conventional paver with sand and a 2 or 3 millimeter joint full is a great system that doesn't move vertically when you drive across it. We use it for intermodal terminals and all kinds of major container ports. You go to Rotterdam, they have regular pavers. You go to San Francisco, to Singapore, Montreal, and Canada, they all use pavers because they are hard and durable. When we make them permeable, those are impermeable pavements. To make them permeable, we have to move the joints a little bit wider. And so when we move the joints wider, we don't put sand in there because I lose the ability, the sand will just kind of roll over each other, and so it'll move back and forth. So we put an aggregate in there, some chip layers, basically, something that's going to be 9.5 millimeter or 6 millimeter, 5 millimeter or minus kind of thing. And we don't want it too wide because then we're not going to have the same problem we have with the conventional with the sand if they're too wide. So we specify it. We've got little spacer bars on the pavers to make sure they all pack together exactly the same way. And so again, just local materials, some of your concrete specs are more than suitable for this kind of thing. Installation of the pavers. Ultimately, we want people to make sure that they're installing them properly. In terms of the lines that we have on them, we always specify a mock-up to make sure the contractor knows what he's doing. Cutting them, this is one of my biggest concerns and always has been for any kind of segmental pavement system. I will not allow you to put a paver on the road surface that is less than 40%, I use 40% of a full-size paving unit. I will not have a sliver like you see in the bottom left-hand side there where it says no. No, I mean, ultimately you need to make sure things are parallel to each other, and you have ways of changing the field of pavers at those transitions to make sure that you never have to put a paver in that's more or that's less than 40% of the size of a full one. And I only use that because I want people to be able to use half-size pavers ultimately. So really, really, really important because those are usually the places where I see things fail. Joint aggregates, talked a little bit about them. You see what you see in the hand there. We need them to be hard and durable to provide the shear force resistance from the pavers, and we need them to be open graded to get water in. This is extremely important because in some cases I could have 2 meters of permeable pavement, and I can't get water through the surface into the permeable pavement because maybe the storm intensity is so high in the middle of a 24-hour storm that the infiltration capacity of the surface cannot accommodate water getting in, and it will flow off the permeable pavement. Right. And so that happened. A project I'm working on in Texas, in a 100-year storm, I cannot get the water into the pavers fast enough. The permeability initially is, we specified 2.5 meters of water per hour, not per 24 hours, 2.5 meters per hour. We design it for 250 millimeters per hour. because we expect that we're going to get some clogging of the permeable pavement over time. This is what it looks like when you're finished. Railway ballast size aggregate on the bottom. We've got a 10 centimeter thick base layer. This is the yellowy colored aggregates, crushed rock, and then we've got the bedding layer above that and the joint material in the surface there. So many times the joint material and the bedding material will be the same aggregate, exactly the same. But again, lots of details in the standards that talk about this. Supplementary surface drainage. So here's a situation where during a rainstorm, a very high intensity rainstorm, even though my pavers are quite permeable, I may not be able to get all the water in during the highest intensity of that storm. And so I want someplace else for the water to go. It may flow off the surface. In the left-hand side there is a cutout in the curb. This picture actually shows it a little bit better here, where you have a curb cutout, so the water will flow off the pavement surface into the aggregate and then underground into the layer below. This particular one is one from out in the west coast of the U.S. in Oregon, and the entire parking lot you see on the left-hand side of the top all flows to the back corner. The back corner, you see the picture that's on the right-hand side. There's a small ditch that goes across the back of the parking lot. The water goes into that. There's plants that love being in the water and use the water and then evapotranspire it out. And then in the back corner, there is a stormwater pond. I've been to this site 5 times in the last 15 years, and I've never seen water in the stormwater pond. So eventually the water, it's a great design. Others here, this one on the bottom right-hand corner, you see a catch basin in the corner. Why have I got a catch basin and a permeable pavement? Well, that's my supplementary surface drainage if the water can't get in. There's so much coming down that I want to move it. I don't want it to be staying on my pavement surface. So I move it out into a stormwater pond or something like that. Tons of different examples of this. This is from a bank building, parking lot, front area where there's a couple of chairs you can sit on, and then there's the rocks you see there. If you follow the rocks around the corner, you'll see a little slot drain, and then so when water overflows, it'll go through that slot drain. We include tons of things like rain gardens. We accommodate all of these kind of things in the surface that may add some additional cleaning to the water, for example, and combined with water flow abatement. Dealing with slopes, we've got ultimately, we want to control the water that's under the ground. I showed you the baffle. So this is basically a notched subgrade to the right of that red line going up the middle of the photograph. The aggregate was put down, the aggregate material, the baffle was then folded over, so the impermeable liner was folded from the right to the left. We then covered the whole thing with aggregate, and there it is under the ground. In this particular case, they included a bidirectional geogrid as well. I said I'm not a particular fan of that. Again, when I need to use one, I will. Contractors hate to work with these things during construction as well. Utility conflicts, here's basically what you do with utilities. So we're able to wrap them some cases. Some utilities are a little bit concerned about them, so we certainly can do that if necessary. Maintenance of permeable pavements, I mentioned already that all pavements need to have maintenance activities with them. And so and this is something I usually do. I'm doing a training session tomorrow, all morning, actually, for a local city. And they haven't built their pavements yet, but they wanted the maintenance training for their parks and recreational folks and for others to understand, what we need to do with our permeable pavements once we have them built. And so ultimately, we want to make sure that they're structurally sound, they're structurally adequate. And this is like a pavement management inspection like you would do with any other kind of pavement for that matter. And then we also have to deal with surface infiltration. So we want to make sure that water goes into the permeable pavement system. Guidelines, ultimately, we want to try and achieve and maintain around 250 millimeters per hour of permeability throughout the life of the pavement. As I mentioned, it starts out at 2,500 millimeters per hour or more. It depends on the pavers, the sizes, the spacing of the joints, and the aggregates in the joints. That's what depends on it. But at the beginning, you just take a bucket of water, throw it on, and it's gone. It goes away immediately. Secondary drainage features, things like subdrains under the pavement, outflows on the surface in a very high intensity storm that may occur, et cetera, et cetera. And there are pavement management type tools, such as ASTM E2840, which were designed and published to look at permeable interlocking concrete pavements. And I'm the author of that, in fact, the original author that submitted that to the committee for publication. So in that publication, we have basically pavement condition evaluation activities to calculate a pavement condition index for a paver or a segmental paver-based system. These are the elements: surface clogging, depression, rutting, faulting, damaged pavers, edge restraints, excessive joint width, joint filler loss, and horizontal creep. And then within each of those, there are some guidelines that talk about what you should do. And so surface clogging, ultimately, we go to the standards. We want to make sure that we're getting water going in. We've got standards to test them, including devices like this, very simple surface permeability test. I've done hundreds of these myself. We're taking a container of a known size. We've got some putty that we put on the pavement surface, and we pour water into it, ultimately. And depending on how fast that water leaves the pavement structure, you have an idea what the permeability of the pavement surface is going to be. The infiltration test for pavers, PICP, is ASTM C1781-13. And ultimately, we have monitoring programs that say, okay, for all those issues that we have there on the left-hand side, how often, what should you do, how should you repair it, when you should repair it, and what frequency you should inspect it, basically. And so this is what I'm doing tomorrow with this group in Ottawa, Canada, is walking them through more details than I'm showing you here. I don't have the time today to show you all the details, but ultimately, this is the kind of things that we put in place, and we train them, and we provide them with PowerPoint presentations and things like that, so they understand what is actually needed. In terms of surface cleaning, the thing, I said all pavements need maintenance. The ways of cleaning them or keeping them clean can vary substantially. And so we have what we call preventive maintenance, and we have restorative maintenance. These, what you see here, are primarily restorative maintenance items. So when you really screw up and it's 15 years later and you've done no maintenance at all, you want to restore the permeability, you need equipment that looks like this. There's a local professor here, Jennifer Drake at the University of Toronto, who's done tons of work on maintenance of permeable pavements. And her and I worked together on the ASCE standard as well. I recruited her to be one of the members of the committee because of her maintenance experience. And we're finding now that, though, if you do some minor things like these things in advance, you don't need to do the restorative maintenance. And so, and in fact, Jennifer and I and a woman down in San Marcos, Texas, last week had a meeting to discuss the use of a small, they call them sharks or Roombas, or I don't know, those little things you use to clean in your house. It's a remote control machine that goes up and down. And we tested it on a driveway about 2 weeks ago, and we're testing it next week on a mock-up of a pavement that's going to go in at the University of Texas at Austin. And so we're going to start some research on using very small sized vacuum type things or sweeper type things. And this can be done manually as well. I mean, if you have, many people don't have access to these types of equipment, obviously, because they're fairly specialized, but smart contractors are getting in the business and providing these services now to municipalities. And so they're making good money on it. Or you can, this is not, I wouldn't call it necessarily a make work project, but I mean, it can be done very simply as long as it's done at a timely fashion. So it needs to be done before we have to have the need for some restorative equipment like these kind of things. These work really well. I can remove the aggregate from the joints completely, clean it, put it back in the joints ultimately. And so if you have to get to this, you don't want to get to this point, but if you have to, there's ways of fixing it at the end of the day. And segmental pavers are easier to fix than asphalt or concrete, because the fact that only about 10% of the surface area of the unit has got space in it for water infiltration, the pavers themselves are not permeable. Whereas for asphalt and concrete, you got a much higher opening surface, by 25% surface, and it's harder to get a vacuum in those systems to make them work. Paver repair, just some examples here quickly of how we deal with these individual paving sections and whatnot. Maintenance and rehabilitation, this is just a sequence of slides I'm going to show you of someone actually doing a utility repair on Berkeley, Alston Way in Berkeley, which I showed you the design of earlier. And so we had to access the utility. So we document step 1, step 2, step 3. What do? You bring aggregate into the material. You remove the pavers. You stack them beside the repair area. You fix the base or the bedding layer if you need to add some materials to it. You may remove some. It may be too high, too low, or whatever. Ultimately, screed the base layer flat and then put down some screed bars. And so now we're going to put the bedding layer on top of these pipes that you see. So there's them putting a bit of aggregate on top of the pipes. They're now bringing in the aggregate for screeding for the bedding layer, and he's just literally pulling it across the pipes that are in there. Once they're done, they remove the pipes, fill in the space where the pipes were with a small trowel. Return the pavers to where they belonged. Here's them taking a few more, putting them in, replacing them. The area is getting smaller and smaller as I go through these slides here. And ultimately, when you finish at the end of the day, we're going to make sure that the last stone goes in. This is the important part. What went in, what came out needs to go back in. And frequently I'll see one or two of them still hanging around someplace. A contractor didn't, use up one of them. In fact, there's one you see actually in the wheelbarrow there as well, but it didn't come from this location. So ultimately, put our stone aggregate back on top of it, sweep it into the aggregate, and then clean up basically, and the final pavement surface will look like this. And so the right was the undisturbed, the left is the utility area that was there. Not like repairing asphalt or concrete, you'd never know you were there. So this is not very complicated in making this kind of thing happen. Utility restoration guidelines, ultimately we have to keep everything clean, and we don't want to have bits and pieces hanging around on the surface here. Ultimately, we want to make sure there's no debris left. All the aggregate that needs to be in the joints is going to get into the joints. We want to make sure that we have areas that are parallel. If we're close to things like a curb, we remove the pavers that are adjacent to the curb. They're probably going to move during construction if not properly restrained. We don't want to make the joints wider than they should have been in the first place. And so ultimately, it's very simple. It's not complicated, step by step. And when we train this stuff, we explain to people how they do that. At the end, they think that's really not that difficult to do. And this goes, and the nice thing about it is that you don't even know that you were there. Utility cuts can take away a lot of life of the pavement system. And so we don't really want that to happen. If it's properly restored, there's virtually no cost associated with it. I actually am just finishing several research reports up right now on life cycle cost comparisons of permeable pavement systems. Utility user delay cost quantification, utility cut repair quantification. Another one I finished a couple of years ago was on the off-road benefits of permeable pavement systems. So this was, we have the ability to infiltrate water, but what are the other elements that are associated with it that save us money? And things like catch basins and underground piping systems and smaller storm area, smaller storm ponds, for example. Painting, we don't need to paint the pavement surface. We can use color pavers, for example. Installation of speed bumps or humps or whatever we call them. And the differences between doing that on a paving system versus a conventional asphalt or concrete system, and what are the life cycle cost benefits. And there's a huge spreadsheet that helps you calculate those. Just give me 1 second for a drink. Too much talking in a row with not much lubrication. Preservation recommendations and lesson learned. Just a few more pictures here to show you. Ultimately, we don't really want to paint the paver system. So what you see on the left, I took that one in the Netherlands, which was their handicap parking zone, which they made with colored pavers, perfectly fine. The one on the bottom there is from my project out in Hawaii, in Oahu, which was the Holy Trinity Church, where we had arrows because we had one-way traffic. And so a different color was used to designate the arrows. Not so thrilled about this simply because the edges, you can see there's some cut units on it. Markings going across for a crosswalk. Those are just colored pavers, colored permeable pavers, in fact, in that situation. Same roadway, centerline markings. You can see they've used a single band and a double band here of color paver systems. Bicycle parking or motorcycle parking in this particular case. Each of the stalls you can see has been separated by individual pavers here, and so each of those things will show a little bit something different, so that you can designate the areas. And so these are easy to do, very, very simple to do, and you'll never have to paint them again as well, which is fantastic. Ultimately, though, making sure that it's going to last, designing it so that we don't have materials washed off from one pavement type to the other. So in this case, from the dense graded asphalt onto the permeable paver system, you can see some winter sand in this case that is moved into them. In North America, we do have winter sand we use for grits basically on the pavement surfaces. And so it is not very fine, because then it will be like toothpaste, and it's not too coarse to break windshields. So it's actually closer to the gradation that we use for the actual pavers in the joints. And so sometimes this is okay. because we just don't want really fine material in there clogging the joints. In terms of vehicle types and things like that, the vehicle you see on the left was from an alleyway I took in Richmond, Virginia, and it was the garbage vehicle. And fantastically, I could see the pavers moving under the load of this vehicle, but coming right back after the vehicle passed over it. And so the method of handling load is different than a conventional dense graded aggregate pavement, because you don't get the shear, all of the big rocks and little rocks and small rocks all together providing shear capacity. These are all providing it through point to point contact. And so it absorbs some of the load and then kind of springs back, which is, based on my observations, is pretty interesting. When you do have heavy vehicles like the tank you see on the right, obviously you need to accommodate it and design the pavement to handle those things. They did end up building 4 of these battle command centers throughout the United States using permeable pavers, which was pretty cool. What else do we have here? Okay, this here is a video of fire truck basically dumping fire hose water on the pavement surface, and I'm not really showing you that just to see the fire hose. Look at the bottom right hand corner of it, and so you'll see bits of the aggregate on the surface of the pavement there. And so that's something that you don't want to have happen. So if you're going to spray wash something to try and clean it, you can do that, but don't dislodge the aggregate necessarily. Or if you do, you need to replace it after the fact ultimately. So I'm just going to skip to the end of that there and then move on. And that's what typically we do when one of these projects is finished. We have these videos, bring the fire department out and we show them how much water they can actually incorporate. But my view here is the bottom right corner where I say I don't want to have the aggregate washed out of the joints. And that's what's happening under that huge stream of water. Education is important. This is actually a pervious concrete area near a park near Boston Logan Airport in Massachusetts in the US. And those bags contain crushed up tire rubber particles that they spread on the soccer field, on the football field, the pitch. And no one told these people, the maintenance people, about this new pavement, this permeable pavement. Well, under all of that rubber that they dumped is basically a permeable pavement, and obviously not much water is getting into that particular location. So we see that a lot. Power washing can be done, certainly. It's not highly recommended because you're going to dislodge the aggregate in the joints most likely, depending on the angle you're using on the power washer. But you can actually dislodge the stuff in the joints that have clogged it, and then simply clean off the aggregate and spread and use a broom after it's dried and spread it back into the joints. Certainly, you don't need to replace it necessarily. You just need to make sure that there's enough aggregate in the joints. Things like landscaping materials, masonry, things like this, are wonderful. We usually use something like one of these education signs out there to show people what a permeable pavement is. The one on the left there comes actually from the permeable pavement guide. Here you see that Environmental Resources Institute section. The one on the bottom is the one that we designed for the porous asphalt pavement in the Quebec. And so this one is in French, obviously. And the one in the top right-hand corner is actually from a parking lot at a bar near a river in Oahu, in Hawaii. And that became a very interesting experience for me, because my wife and we vacation in Hawaii quite frequently and have been there 30 years, I think 30 of the last 35 years. And while I was there, met some folks and wanted to build permeable pavements. And I gave some presentations in a workshop like this one, and was told basically at the end of the workshop, taken aside by the one of the folks there from the Army Corps of Engineers. And he said, "Dave, you're wasting your time." He goes, "There will never be a permeable pavement built in the state of Hawaii. There's no geotechnical engineer in this entire state who will ever sign off on a permeable pavement." There's at least a dozen there now. Several were designed by me. When I was there on vacation, I actually got paid to go there, which was kind of a good thing for me. In 2019, in the summer, actually, I participated in a half-day workshop hosted by the water stormwater folks in Honolulu. Several technical papers for the low impact design conference that they had there, and now they're building more. And so geotechnical engineers tend to be very conservative when it comes to pavement design. Certainly, they're not pavement designers, but a geotechnical engineer will play at pavements, and a pavement designer will do pavements and play at geotechnical sometimes. So ultimately, at the end of the day, this is successful for maintenance purposes. This is that church I mentioned in Oahu, and you see a large parking area behind it. And this was in in Hawaii, and they built the Pearl Harbor Memorial has got pervious concrete. All of the military bases have got permeable pavers on them. The botanical gardens have permeable pavers and all kinds of things. They do get a lot of rain there, obviously. And so they don't have a lot of subsurface drainage. And so this was able to capture the drainage, solve a problem, and then ultimately be used as a functional pavement system. And people don't even know really what it is. They just use it like it's a normal pavement structure. All right, so this is the my final slide, which talks about durable and sustainable solutions. This is about 2-hour drive north of where I am sitting right now, and it's a national park. And so all of the parking areas in this national park are also permeable pavements, and the material below there is actually rock. So water basically goes in and then it flows laterally out to the lakes that are there. So instead of taking runoff, it's clean when it gets back into the lakes. All right, so I am more exactly the time I was hoping to be on, Madeline, and perhaps now we can take some questions if there